In this video, we're going to examine an aspect of the law of conservation of energy called the Work-Energy Theorem. And essentially, this is an aspect of conservation of energy that focuses on the mechanical energy and the relationship between them and the transformations between work and kinetic energy. So the Work-Energy Theorem is simply defined as the work done on an object being equal to its change in kinetic energy. Or that is to say that one of the things that you can do with work is that you can change the kinetic energy of an object. That means that you can speed it up or you can slow it down. We can actually, before we write the equation for Work-Energy Theorem, we can actually derive this from a previous equation that we looked at back in kinematics when we were looking at accelerated motion. And to do that, I'm going to start with this equation, that the square of the velocity is equal to the square of the initial velocity plus 2 times the acceleration times the displacement. So starting with this equation, we'll derive the law of conservation of energy in an algebraic sense. So I'm just going to do a little bit of algebra with it, nothing illegal. Whatever we do to one side, we will do to the other side. And the first thing that I'm going to do is I'm going to multiply by the mass. So I'm just going to distribute that into all of these properties. That gives me mv squared equal to mv naught squared plus 2 MAD. And the next thing we're going to do is we're going to move that 2 over to the other, and you'll see that the effect of that, by dividing by 2, we'll put a 1/2 in front of each of these 2, and then this will turn into the kinetic energy. Okay, and so now there's just a little bit of cleaning up. I'm going to move this over to the other side, leaving the MAD, and on this side 1/2 mv squared minus 1/2 mv naught squared. So there you can see the change in the kinetic energy. Here's my initial kinetic energy, and here's my final kinetic energy. On this side, this is obviously the force acting on the object. So MA will be the force, and as a result, what I get is the final kinetic energy minus the initial kinetic energy is equal to F times D, or in other words, the change in the kinetic energy is equal to the work. And so what this basically is showing us is that in mechanical energy, it's not a law. This is why it's referred to as a theorem. It's not a law. It just simply shows that the work that's done on an object can be used to transform into the kinetic energy or vice versa. Kinetic energy can be removed from an object by doing work on the object. So let's take a look at a few example problems to see how this may work out in just a practical sense as you're working your way through physics. And let's start with this problem. So we'll have a 235 kilogram motorcycle producing a thrust of 1500 newtons over 80 meters. And what I would like to do is to calculate the final velocity of the motorcycle. So I can see I have the mass and the force and the displacement. So I have the work side of the equation, and I have part of the kinetic energy portion of the equation. And what I'm missing is the final velocity, which is of course in the kinetic energy. So I'm going to go straight to the work-energy theorem and say that F times D equals 1/2 mv squared minus 1/2 mv naught squared. However, in this case, we're going to assume that the motorcycle was at rest in the beginning. It doesn't explicitly say that, but we're going to take that to be the case. And so we're left with F times D is equal to 1/2 mv squared. The kinetic energy of the object is produced by the work that was done on it. And I'm going to solve for v squared. So that would be 2 times fd divided by m. I multiplied by 2 to remove the 1/2. I divided by m to get that over to the other side. And now I have v squared by itself. So in this case, that's 2 times 1500 times 80, all divided by the mass, which was 235. And if you put that into the calculator, 2 times 1500 times 80 equals divided by 235. That gives us 1021.27. And then in order to get the velocity by itself, we'll just square root, sorry. And the square root is 31.95 or 31.96. Okay, and then reducing that down to the correct number of sig figs, we have 3 and 2, and actually technically this has only 1. We'll cut this down to just 2 sig figs. .32 meters per second is the final velocity of the motorcycle. Okay, and this is like a very practical, like real world problem. Typically in the equation, what you're going to be asked to look for is you're usually asked to look for either a velocity, you're asked to look for what was the displacement over which the kinetic energy changed, or you're being asked what was the force that caused the kinetic energy to change. So let's take a look at another variation of this problem. We'll just move this out of the way. And we'll try this problem. So Jasmine's attempting to pass a slower moving car on the highway. She accelerates her 1,540 kilogram car from 25 meters per second to 35 meters per second over a distance of 395 meters. What you're being asked to do is to calculate the additional force produced by Jasmine's car during the pass. You're being asked for the additional force because the amount of force being applied to the car to allow it to travel at 25 meters per second is not given. We don't know what the value of that is, but what we can figure out is how much extra force was applied to allow the car to make the change to its velocity. So again, I'm going to go straight to the work-energy theorem. F times d equals 1/2 mv squared minus 1/2 mv naught squared. And what we're looking for this time is the force. So essentially what's going to end up happening is I'm going to have F is equal to 1/2. Now I'm going to do something a little different here. So let me just show you how we can kind of clean this formula up. You do need to square this before you make the subtraction. So you can't subtract the velocities and then take the square of that and think that that would give the same answer. So that's an illegal operation algebraically. But what I can do is I can factor out the 1/2 m, since that appears in both of them, and then I can do v squared minus v naught squared. That makes it a little bit easier to make the calculation. It's not required to do it, but it does make it a little bit easier. So 1/2 1450 times the quantity 35, the final velocity, minus 25 squared, I should say 35 squared, minus 25 squared, which is the initial velocity, and then that all needs to be divided by the distance, which was 395 meters. So we'll bring in the calculator and we'll just go ahead and do this all at once. So 0.5 I should say, times 1450 times the quantity 35 squared minus 25 squared is equal to, and we'll divide by 395. So we end up with about 1100 newtons. And that's it. So we looked at an example problem where we solved for velocity. We looked for an example problem where we solved for the force that was being applied. And we'll take a look at one last question, and that is a question where we look for the distance or the displacement of the object. So in this case, a 2120 kilogram truck is traveling at 18 meters per second when a car pulls out in front of the truck 44 meters ahead. The maximum braking force is 8,000 newtons, and you are asked to determine whether the truck can stop in time to avoid the car. Now, it might not be obvious because it does look like you have mass, you have velocity, you have force, and you have displacement, but very important to recognize this is not the displacement of the truck. This is not how far the truck traveled before it came to a stop. This is simply how far away the other car is in front of the truck. So I actually need to solve for the distance, and then I'll compare that distance to this number, and if it's less than 44, great, and if it's not less than 44, then that's bad news for the truck and for the car. So again, we're using the work-energy theorem. F times d is equal to 1/2 mv squared minus 1/2 mv naught squared. In this case, the truck was traveling at an initial velocity of 18 meters per second. This is my initial velocity, but there is no final velocity because the goal of the truck is to stop, right? So this gives me the final velocity as 0. So in order to determine the displacement, I would say that d is equal to minus 1/2 2120 times the initial velocity of 18 squared divided by, and this is kind of an important thing to think about, minus 8,000 on the bottom. I say minus 8,000 on the bottom because this is a braking force. So it's not going with the motion of the car, it's going against the motion of the car. So if we take the motion of the car to be positive, which I did, then the braking force would have to be a negative force opposing the motion. So taking that to the calculator is, I'm just going to ignore the negative signs since they're going to cancel out anyways. So 0.5 times 2120 times 18 squared equals, divided by 8,000, gives me a distance of 42.9. meters. And so then we can see that the truck can safely stop. So my final answer is the truck can stop with 1.1 meters to spare. And so obviously there's maybe even simpler problems with the work-energy theorem where you may be asked to just calculate how much work was done on this object and you use the kinetic energy to figure out how much work was done. Or you may be asked how much kinetic energy did this object gain, and instead of calculating it by 1/2 mv squared, you would use the work side to be able to do it. So these two are interchangeable. It's kind of similar to like the impulse equation where the impulse is equal to the change in momentum. And so you can use kinetic energy, the change in kinetic energy to find the work, or you can use the work to find the change in kinetic energy. And that's the work-energy theorem.